participants for the panel discussion on quantum safe and enable security at Annual Information Security Summit 2020. I'd like to welcome experts from IT, academia, and government sector. I welcome Mr. Vivek Shenoy, Chief Technology Officer, QNU Labs, who will be moderating the session. I also welcome Mr. B.K. Murthy, Scientist, and Group Coordinator, Ministry of Electronics and Information Technology, Government of India. I also welcome Dr. Urvashi Sinha, Professor, Raman Research Institute, and I welcome Dr. Arpita Maitra, Assistant Professor, TCG Crest. Once again, a very warm welcome to you all. Handing over the session to the moderator. Over to you, sir. Over to Mr. Vivek Shenoy. So your voice is not audible.
Oh, okay. Sorry, I was on mute. Thank you, Manjesh. Welcome everybody to this session. We have three very illustrious people on this panel, and I'm hoping that in the next 45 minutes we will get some good insights into what is happening both in the security space, in quantum technology and quantum key distribution, and specifically the initiatives by the government in this space. So I would like to start with Professor Mitra. So you've been working with quantum cryptography and cryptanalysis. The question that I always hear is there's a lot of confusion on the difference between what quantum computer is and what quantum cryptography.
Yes.
I would like you to give us a little bit of a background between, or a difference between the two, so that we kind of lay out differences between these two technologies.
Yes, during my talk, during the discussion, I will answer that question.
Sure.
So, in the discussion, I like to share some of my glimpses on security towards quantum safe cryptology. So, the discussion, the outline of the discussion will be as follows. So, the outline, first we will discuss quantum computer and classical cryptography, how quantum computers affect classical cryptography, the NSA National Security Agency of US, that recommendation, NIST National Institute for Standard and Technology Post-Quantum Cryptography Portfolio, QKD Basic, Quantum Key Distribution, that basics, and Symmetric Cryptography. After that, we will discuss some basic questions and what should we explore in future.
Sure.
So we know that Shor's algorithm, we are very familiar with Shor's algorithm, and we know that this algorithm is used in cryptanalysis of RSA, Samir, Edelman, and public key cryptography and ECC elliptic curve cryptography. And Grover's algorithm is exploited in symmetric cryptography, and due to Grover's algorithm, the effective key size will be reduced to half in case of symmetric cryptography. And Google CEO recently claimed that within 5 to 10 years, that fault-tolerant full-scale commercial quantum computer will come into the picture. So we need quantum preparedness from cryptography aspect. I think so. Now, in this direction, NSA recommended the following. For those partners and vendors that have not yet made the transition to SUD-B algorithms, that is elliptic curve cryptography, we recommended not making a significant expenditure to do so at this point, but instead to prepare for upcoming quantum resistance algorithm transition. So this policy clearly states that we should focus on post-quantum cryptography, and this also signals that commercialized quantum computer might not be a distant dream. By post-quantum cryptography, we commonly imply classical cryptographic public key algorithms which are resistant against quantum attacks, such as lattice and code-based cryptography. Considerable research is going on in this direction, and NIST third round candidates post-quantum code portfolio has been announced, and this is the URL. But those are not as efficient as RSA or ECC. but those may be shortly used in commercial domain in case quantum computers arise. Another avenue is quantum cryptography. Now I come back to that question Vivek asked, that what is the relation between quantum computer and quantum cryptography. So well, quantum cryptography has two parts, quantum communication parts and quantum computation parts. Quantum communication, very good example is QKD, and quantum computation is exploited for cryptanalysis of different ciphers, symmetric as well as asymmetric ciphers, for finding collision of a hash function, for cryptanalysis of error correcting codes, etc. For example, if we consider symmetric ciphers, then evaluation of quantum cryptanalysis requires quantum version of that cipher. And exploiting quantum superposition and quantum parallelism, we can mount the quantum attacks, which is actually Grover or Simon or combination of those. And we can mount that attack with the help of quantum computer. So this is the relationship between quantum cryptography. So quantum cryptography cannot be done without quantum computer. So and we know that quantum communication is also a part of computation. So quantum communication devices also a subset of computation devices. So without computational devices, quantum cryptography won't be successful. Now, quantum. So now, so in this regard, actually, I generally don't like to define my work when I am presenting something. But for better understanding, we referred these two papers where we evaluated the complexity and estimate the quantum resources need for the key recovery attack on two lightweight block ciphers, namely Simon and Speck in IBM Q quantum computer. So these two papers might be example how we can exploit quantum computers for quantum cryptography. Okay, now QKD Basic. I am not going into the detail. So quantum key distribution has two distinct parts. One is classical, another is quantum. Quantum part deals with qubits exchange and measurement, and classical part deals with error correction and hashing. Attacks are generally considered on quantum part. However, classical part, as we are exploiting hash function and classical hash function and error correcting codes, so that might not be quantum safe. So we need to study those very carefully before implement those in a QKD protocol. Now, symmetric cryptography, I already mentioned that for any symmetric crypto system with n-bit secret key, the key can be recovered in order of 2 to the power n/2, exploiting Grover's first algorithm. To guarantee the required security, a useful heuristic is to double the key length. However, to implement Grover, one needs to design the quantum version of that cipher. Several papers in top cryptology conference connecting, improving and implementing these results. Now, basic questions. So, India is third world country, and generally third world countries are not front runners in fabrication of quantum equipment. So, as in case of classical computation and communication equipments, it is expected that they would purchase quantum equipments from external agency only. So, the very important question from my aspect is that how we can evaluate that third-party quantum equipment, so that this is quantum at all or something else. We are taking some example. We are considering some example. Suppose QRNG. We purchase a QRNG quantum true random number generator from a third-party vendor. Then this is a finished product. So how can we realize? How can we understand that this is the quantam at all? Because seeing the output string, we cannot differentiate this from a pseudo-random number generator, because the pseudo-random number generator, the output cannot be computationally and theoretically distinguished from a random number generator. So how can we understand that this is a quantum thing at all? So we have two options, we have two ways. One, we have to somehow get into the circuit of the product or the components and verify whether it is a quantum product or not. And two, go through the documents or codes for analyzing the facts. In this direction, our interest should be to access the interface with each component of QRNG to obtain the corresponding output and to analyze those to verify the quantumness as well as underlying security of the product. Now, in this scenario, what we should explore? One natural thing, that actual implementation of quantum algorithms, and specifically we should be interested in cryptanalytic, implementing the cryptanalytic techniques and how to implement those in noisy intermediate scale quantum technology. We should estimate the resources required to perform that attack so that whenever actual fault tolerant full scale quantum computers come, we can implement those attacks immediately. Now, lots of classical pre-processing and post-processing are required before and after quantum module. Example, QKD. So after quantum part, we need error correction and hashing. So such I already discussed that such classical modules also should be studied very carefully for avoid any loopholes, any security loopholes in the product. So these are the all which I like to convey. So thank you.
So you on mute.
Yeah, I'm sorry. So I have a couple of questions on this. You said when we look at a device like QRNG, you would have to do in-depth analysis of what is inside and how do we determine that it is actually random and using quantum techniques.
Yes.
Now, if you buy a third-party equipment, why would anyone let you do that?
That is the question. Yes, that is the question. But for security reason, if we that is a finished product, so there should not be any way that I can evaluate. So that is the question. That is my question. So how can I evaluate? How can our government can evaluate whether this is quantum at all? But this is a finished product. We only get the output string, and that output string cannot be differentiated from a pseudorandom generator output. So how can so that is the question. That is the basic question I have.
Okay. And just very briefly, what would be the other uses of quantum computers? You have highlighted, for example, cryptanalysis, breaking of ciphers, and so on. So, in non-cryptography field, what would be their uses?
Yes, so in that Grover, Simon, and all those algorithms can be Doyle-Zosa. So those algorithms can also be used in finding that in biology, in medicine. So there are lots of uses except cryptography also. So quantum computer. But the main thing is we need full-scale fault-tolerant quantum computer.
Okay, got it. And one final thing from me. So you said if in case quantum computers arrive, PKC would be something that would be very useful. So the threat of quantum computers being able to crack today's cryptography, is it actually real, or are we kind of imagining the fear?
No, actually, if a full-scale quantum computers means actually we need that we can estimate the resources to perform Shor's algorithm in a quantum computer. So if and suppose we need X number of qubits to perform Shor's algorithm to break today's RSA crypto system. So suppose we have that, we can build the quantum computer with that x many qubits. Then using that quantum computer, we can break RSA. And today's crypto system, today's publicly key infrastructure actually uses this RSA and ECC. which are based on discrete log and factorization of a large number. So using that computer, we can break that. So but again, that thing is that we need fault tolerance full scale quantum computer.
Okay, got it. Thank you so much, Dr. Mehta. Now move to Dr. Murthy. Now, specifically, you work with MAITI and part of the government initiatives. And quantum computing and cryptography is generating a lot of interest. And within the government, worldwide and within the government, there's an initiative for quantum research. Now, brief us about the key government initiatives in this area.
Thank you very much. Good afternoon to all the speakers, learned speakers. I would like to share my screen. Are you able to see this screen?
Yes.
Yeah. Okay. Thank you very much to the organizers for giving me this opportunity for the AISS 2020, and thanks to DSCI and NASCOM. I would like to just touch upon what are the cybersecurity challenges in the post-quantum era. Suppose if we get the quantum computer in the near future, what will happen? So if quantum computers were here, so all these standard cryptography algorithms or security algorithms, LGMAL, RSA, elliptic crypto, and these can be easily broken within no time. So lattice-based cryptography also candidates for replacements exist, but still not very much studied, and then these also can be broken very immediately. So even the double the key length of the common symmetric cryptography algorithms, AISS and SHA-1, etc. These also can be easily broken if the quantum computers are available. That means if quantum computers were available today, no security algorithm, current security algorithm would not work. So what would be the effect of this? If the products and services and business functions, etc., all will have security problems. That means the RSA algorithm, DSA, AES, 3-dash, SHA-1, SHA-2, these algorithms may not function very well, and it will not provide the desired security level. Accordingly, your secure web browsing or auto updates and digital signatures, all these things may not work in near future. Even the blockchain systems also will have a problem if the quantum computers are available. So accordingly, cloud computing, your payment systems, internet, IoT, whatever the banking transaction that you are doing it, this will get affected. These are all completely vulnerable in no time.
So we would go back essentially in terms of communication.
Yeah, yes.
We would go back about 50 years in terms of communication.
Yes, obviously. So, do we need to worry now, or the quantum computers are around and people, yes, many people have already announced their quantum computing systems. So, how long do you need to cryptography keys to be secure? So, the quantum computers are coming maybe 5 years or 10 years down the line, but what is your shelf life that is required for your cryptographic keys? And how much time will it take to retool or re-existing or migration of your existing algorithms into quantum safe solutions? If these are X years and Y years, and how long it will take for a large-scale quantum computer to be built? If this is X plus Y is greater than Z, then obviously you have to worry now. So what is the business bottom line? People say that even if it is availability of a reliable quantum computer of 50 qubits makes you worry from security angle. So even the largest computer or security algorithm that you are having, even it can be broken within just 20 qubits of the qubit computer, a quantum computer. However, it should be reliable and robust. So right now, plan for migration will be expensive, disruptive, and lead to vulnerable implementations because the standards are yet to arrive and the quantum computer algorithms are need to be standardized. So the prediction is in the next 5-6 years, organizations will be differentiated by whether or not they have a well-articulated quantum risk management plan or not. So quantum cryptography will help in two things: cryptography involving quantum mechanics, that means either security against the quantum computer or using quantum mechanics in crypto protocols to make your cryptography algorithms or any security system secure. So quantum cryptography deals with quantum number generation, that I just mentioned it. Quantum key establishment, QKD, is another one. So already Shanghai in 2016 itself, Beijing, Shanghai to Austria, they have established a QKD, already POC has been established. So this quantum network has already been established, and some of these experiments that you see on the screen, these are already available on this and in the lab type, and people are using it in most of the cases. So quantum safe cryptographic tool chest is what you can do is using conventional algorithms and quantum safe cryptography, you can do it. That means post quantum cryptography is the right now people are working on it. And once the quantum computers come, these algorithms can be ported onto them very easily, and this will work. So quantum cryptography is both sets of cryptography tools can work very well together in quantum safe cryptography system. So I'll just talk about MITI initiatives. MITI has set up a Center of Excellence in Quantum Technology Applications. One is at IISc Bangalore, RRI, Raman Research Institute, where Dr. Urvashi Sinha is presenting, and CDAC Bangalore. These three centers put together, they work in various applications of quantum technologies. And post-quantum cryptography, we are, along with CERT Chennai, we have started with, once the quantum computer comes, how the digital signatures will vary. And quantum computer simulator, IISc Bangalore, CDAC, and IIT Roorkee has developed developing this. And quantum computer simulator and hardware machine, that means simulator ported onto AISS machine, CDAC has already done that. So some of these initiatives are coming up in the lab level, and we are ready with various systems. Already 3 or 4 startup companies are also in these directions which are there, and we are promoting some of these activities. So capacity building programs with AWS and CDAC, AISS, and IIT Roorkee for conducting intensive course on quantum computing and these algorithms, quantum algorithms also has been done. A secured QKD over a segment of NKN is now, we are just initiating a project on NKN for a long distance segment of NKN. Can we have a secured QKD over a segment of, say for example, 2000 kilometers from here, Bangalore to Delhi, or maybe Chennai to Delhi. So that means we want to have a secured network that can be useful for many of the clients across the country. So other government initiatives include ISRO using satellite communication for QKD. RRI is also involved in developing some of these systems for ISRO. And DRDO plans for secure communication on fiber, quantum materials, and quantum sensing. And they have a big roadmap for the next 10 years in the quantum computing. And DSP has proposed a mega project on National Mission on Quantum Technology Applications. It is around 8,000 crore project, which is still the approval stage. The DPR has been just completed, and it is on the going for approval stage and various directions. So with these things, our vision is in the long term, you need to have a quantum internet, very safe qubit distribution with moving systems, satellites, aircrafts, vehicles, ships, handle all critical infrastructure and make various payment gateways. All should be in the quantum safe with quantum cryptography and other quantum mechanics, quantum computers enabled. So security is a choice. So problematic choices are: do nothing, my vendors will take care of this and I don't have to do. Or do nothing until NIST standardization is done, or get it over whenever it comes. So some of these either laggard approach or maybe a proactive approach, what we can do is security is a choice. Does your organization have a plan? Who is responsible for it? Think about how these different vendors have plans Does your industry have a plan? And are these plans are useful for you or not? So some of these important things that we have to start it, we cannot wait, we cannot be a follower, we should be the leaders also. Fortunately, when compared to other countries in this particular area, India is not far behind. India is also moving towards the right goal, and then various initiatives have already been taken in India. And India is no longer as a laggard or a follower in the quantum mechanics and quantum technology area. So the choice is ours: embrace the quantum technologies that will help humanity and live in a cyber-enhanced world designed to be safe. So if you want to be in the front runner of quantum technologies, you have to start right from the beginning, now itself. So there are various courses available in various institutions, short-term courses, and there is a dearth of manpower is required, and we have already initiated a lot of capacity building programs from MIT, and various intensive courses are being run, and various research programs have already been initiated. The mega project which is coming out from DST, which is also spearheaded by collaboratively with MIT and DRDO and ISRO put together, we are coming out with a big national mission on quantum technologies that is around 8,000 crores project. The DPR just has been prepared, and now it is under the approval process. Thank you very much.
Thank you, Dr. Murthy. That was very, very insightful with lots of information. Now, I have one question which is kind of orthogonal to what you spoke, and then I'll come back to your points. What are the biggest fears of a security breach in the government sector? For example, we hear about compromises on Aadhaar card or whatever else, personal information.
Yeah, I mean, even some of these critical information infrastructure, banking sector is there, oil sector is there, power sector is there. All these things are very critical information infrastructure are there, and most of the government, the banking sector. So that is another important critical information infrastructure. So all these things need to be safe. So if tomorrow quantum computers arrive, so some of these algorithms can be easily broken, and then you will be nowhere. All these systems will become vulnerable. So that's where we have to start right from the beginning, how to get towards that quantum cryptography and then quantum algorithms need to be. How to make our systems secure. The digital payments, for example. So during the last 2 years, the digital payments have gone at least 800 times exponential increase in the digital payment sector. So with these things, if there are any minor vulnerability, people will become panicked. So we need to provide an assurance to the common man. So when using these digital systems, digital India systems, these are secure.
So in this regard, for example, would, let's say, an RBI mandate that quantum security be used in the banking sector?
Yeah, I'm not sure. But once still it is in the research side. So that is, we are trying to it is still in the laboratory side. Once it is there, yes, people will use it. So for the public, we need to provide a security assurance. Whether you are using quantum cryptography or what cryptography, general public is not bothered. But if there is any security breach, they will become panic. So in order to do that proactively, we have to, from the government side, we have to see that our systems are secure.
True. Okay, so you are providing an assurance to the user that whatever data or transactions that you're doing is safe.
Yes.
Thank you, Dr. Murthy.
That is what we call Cyber Suraksha Bharat. When you are talking about digital India, when you are using digital services for various applications, obviously security is inbuilt into it. That assurance should be given.
Thank you, Dr. Murthy. Now I come to Professor Sinha.
Thank you very much for giving this opportunity.
Thank you, sir. You've said that the 21st century promises to go down in history as the quantum age. However, can we really claim to fully understand quantum mechanical principles? How much do we really believe of what we know? This is a very intriguing statement, and I would like you to expand on this and tell us why you think the 21st century is really the quantum age.
Can you hear me, Vivek?
Yes, I can.
Yeah, great. Yeah, so well, first of all, I think I should thank the organizers for this opportunity to present here at AISS and DSCI and NASCOM and all before going on to your question. So, well, 21st century is the quantum age because you see, in this age, we are actually seeing quantum mechanical principles being applied to everyday life, right? So, I mean, last century, as we would call it, was where all these seminal contributions were happening. So, all the, you know, the discovery of various facets of quantum mechanics and exploration at a fundamental level, that was what I would define the 20th century to be. But now, we are actually using them towards products which will revolutionize our society, whether it's quantum computing, communication, sensing. It is across all sectors, and so this is you know, the age in which we can see the fundamental science and the technology both have a developing you know, the kind of synergy which would definitely not be paralleled by any other domain. So definitely it is the quantum age, and I think all these talks we have heard so far are already proving that to us, right? About the exciting possibilities both at a research level and at a technology level. I think that is what makes me you know, say that.
Sure.
Yeah.
Okay, great. Yeah. So could you tell us something about your
It's a little bit of connection issues. Do you hear, Vivek?
Yeah, we can hear you.
Okay, yeah. So I lost out on the last.
Yes, so I was asking you, could you tell us about your work at RRI and what industry types and products that could potentially come out of the work that you do?
Yeah, so for that, I would like to share a little presentation if that works for now.
Yeah, sure.
So it's working, Vivek? So can you confirm?
It's just coming up.
Okay. And say that it has come up, and then, so
Yeah,
first, yeah, so, so at RRI, I mean, you know, in my lab at Quantum Information and Computing Lab, we're working on different aspects of photonic quantum technologies, and essentially this is a snapshot of various experiments, and please visit this website if you want to know details. And so what we do is manufacture different types of photon sources based on nonlinear optics. And so if you wanted more overview, and people who are listening, if they wanted to know more, have a look at this review article where we have different types of photons. So we work on what is called spontaneous parametric down conversion. So different aspects. One of them is, of course, just related to your first question, which is fundamental tests of quantum mechanics. And so essentially the idea being that now that we are saying superposition is used in computing or entanglement is used in QKD, and so how well do we understand these principles to put bounds on these various principles so that the technological application actually gets more precise. And so that is what summarizes this particular slide, where we are dealing with fundamental aspects of quantum mechanics and quantum optics and understanding them better. For instance, here we have a new technique that we have come up with for quantum state estimation, which again is a very important problem, both from the fundamental as well as the application point of view, right? And so in quantum computing, we are working on what is called higher dimensional quantum computing. So instead of qubit-based research, we are working on qubits and higher dimensions, and that has several advantages, which you can again look up this article, which was written with a general perspective on this. We're working on different types of quantum measurements, again revealing things about the quantum system in between preparation and measurement. Do you hear me, Vivek? Because I do hear myself as well. So my audio, yeah, there is an echo. Yeah. Okay. So, and of course, you know, as I mentioned, different aspects of quantum information processing. So here we have different experiments on entanglement, generating, manipulating the dynamics, the static properties. So all that. Of course, coming to the main point of today's discussion, it's quantum communication security. So we are working on quantum key distribution a lot, and as Dr. Murthy already pointed out, so there are already lots of different types of products available on this on a global scale, and so this is definitely quote unquote the most practical quantum technology. And in that, I'm actually an invited member of this focus group on quantum information technology for networks, where we are coming up with standardization towards using quantum technologies in networks. So this is an effort which is involving experts from different countries. In the quantum communications domain, we are working on India's first project on satellite-based QKD, which is called Quantum Experiments Using Satellite Technology in collaboration with the ISRO. On integrated photonics-based QKD, this is an Indo-Italian project. On long-distance quantum teleportation, there are two projects on this, one under this DST program called the Quantum Enabled Science and Technology, and then we have this Center for Excellence, thanks to MIT, which we are a part of. So there we are doing long-distance teleportation as well as random number generation. So essentially all the different aspects that would be required towards quantum communications in both the chip scale as well as the long distance we are kind of tackling in our projects. So in QKD, we have gone through different types of protocols, whether it is non-entanglement based, which is based on uncertainty principle, so BB84. We have our own take on the B92, where actually we change the protocol. Example of an entangled photon source. These are the actual ones. So we have done the BBM92, for instance, with a very nice entanglement, 0.995. So that sort of is a general idea that, try and get the precision level to be as high as possible so that whatever we are applying it to naturally also has the, ends up having the best numbers. So that is how the entanglement also we're approaching. And so you can have a look at some of our work, for instance, this one. And indeed, this is the one which kind of relates to your other part of the question about, this industry tie-up thing. So we've actually developed a toolkit for secure communication, and it got a lot of attention as well, that whereby, and Vivek would know this, that, we have different types of simulators available for QKD, but none of them actually deals with the fact that QKD is not just about a software thing. It's actually an experiment. It requires, experimental demonstration, and so that comes with physical processes and experimental imperfections. So nothing is perfect, right? And so there is a source, where there's a detector, background noise. So all that needs to be taken into account before you can kind of have an idea about what the key rate and Q-bar will be. So now if I want to, find out what is the best I can do and where can I invest my resources, so then such a simulator is of course very useful, because it will give you numbers which will be more realistic than what the commercially available ones do, because they are developed by software engineers. And so we came up with this simulator called QKD Sim, which actually takes into account the fact that things have imperfections, okay, and the actual processes. So this is following the AGI-Fall model. And in fact, this is something we are very excited about, this development, because of course we see that it has a lot of commercial viability as well as a development, right? And so, and you can see how well, our experiment and simulation, I think the next slide has that, how it matches very well, our own experiment, with what we have generated using QKD Sim. for instance, right? And so in the domain of long-distance quantum communications, while we have, of course, seen Dr. Murthy's slide on this, the global picture, very similar to a slide that I also have. So the idea is that, you can't just use conventional methods to increase the distance, because beyond the point, line of sight is an issue, and fibers don't go very far because you need repeaters. So you need to come up with unconventional approaches to long distance. And so for that, there are, of course, these relays and memories and repeater-based ideas, which we are pursuing under the DST Quest program, which I will skip and go to the satellite one, which, of course, is something that we have been doing now for more than 3 years. As I mentioned, it's the first project on satellite QKD. And so the idea is that, in order to circumvent this distance, you have a satellite, it comes to you, exchanges a key, then it kind of crosses over to some other place, which is thousands of kilometers apart in principle, again exchanges a key, and by performing mathematical operations, these two ground stations, they get linked. So you can have a link over a very long distance by using a satellite as a trusted node, okay? And in fact, this sort of summarizes where you can reach with different protocols. So this is essentially the general idea of going towards what we call a global quantum communication network, where, we will have satellites and fiber and everything connected together by using, a combination of this free space and fiber is where we would see our world heading to, and these are our efforts towards that. This is the, the satellite project, as I mentioned, and here we want to essentially establish satellite QKD between 2 Indian ground stations using an Indian satellite, as well as have a link with Canada that is in the plan, which would be, of course, several thousand kilometers. And so this is our progress. You can see our portable ground stations already. This is one of them, and this is us inside that with our free space optics. The current situation being such that we have the masks on, but then we are very, very enthusiastic, and we are working on the free space experiments as we speak. So Vivek, going back to the question, yeah, thanks. So going back to your question about the industry thing, so industry is, of course, very, very important for us, because, we are scientists, right? So we deal with things at a level where we are very good with proof of principle and carrying out new ideas at the research level. So what we would need to do is, collaborate with industry to get it to a product, right? Because traditionally, we are not people who make products which we sell. We are not very good, and that's why we are not very rich. Yeah. So this is the general thing. But then, you see, one thing we have to understand is that, we don't want to be told this, and I think we are told this a bit too often, that everything is over regarding quantum, so where the science is concerned, and it's all up to engineers now. And I'm sure you're from that background, so I don't mean to be disrespectful, but it's just that, we want a healthy ecosystem where academia and industry collaborate with each other, where the science and the technology can go hand in hand, because just capacity building is not enough for our country. So as Dr. Murthy said, we're already doing many things. So we want to keep, us at a competitive level. We need to have the new ideas also come, which has to come from, academia, right? So then that is my take on, the industry aspect of your question. Yeah.
So I have a question to the audience. The question is, so what are the practical, when can we expect the experiment setup that you have done in the lab as a product that is available for general use? What is the time frame that you're looking at?
Well, so far as our protocols are concerned, they are definitely very much, available for general use. But then, of course, we are doing our developments under some projects which are granted by certain agencies. So, of course, there is something there in terms of, this is a research development that we are doing. But then, we are also working on random number generation, as I mentioned. And so things like this, we actually see that because we are working on new ideas towards that. These are things which will be, already at a level where it can be used by various agencies who are interested in doing that. Whether and this chip-based QKD, these are all things which, of course, are more aimed towards usage by people other than just scientists. Whereas, of course, if you talk about satellite-based QKD, that is, of course, involves the satellite, and it involves the satellite agency. So that is really, that is a bit large scale. But what we need is, industries to come up which actually make things in India, whether it's the fiber, whether it's the optics. But that is what we're lacking, the electronics. That has to be built here. Otherwise, we are wasting a lot of time in importing many things. Because, we don't have things made at a level still, which is at the same level of precision as, let's say, I won't take names of companies. So this is what we need to really encourage, so that we can have this indigenization at that level. So we are not going to make lenses and mirrors, but then companies should do that to aid, that is very essential. It's not, everybody doesn't need to work on the protocol, but then if these things happen in India, then we will really do well.
Yeah, which brings to your point that there has to be very healthy collaboration between academics and the industry, because
Absolutely.
both have to work very closely together for any progress to be made.
Yeah.
All right. So specifically at RRI, do you think the reverse works as to how can private enterprises support your work?
Yes, I mean, in fact, that is related to the point we just made, that private enterprises who are working. So the idea is that we would really like to work with agencies who are manufacturing different elements which are coming together for our science, right? Because we want to concentrate on the science development, because that's what we really do better. Let's put it that way. We don't do these things very well. So, if indeed there are people who are thinking of, making correlators, for instance, an example which comes to my mind, FPGA logic, which can be, at the picosecond resolution. Still, we have, it's thousands of euros. And we have such products, but, these are the kind of people we need to come together towards, a QKD protocol or a random number. So these are all very important building blocks towards all these ideas, whether it's computing as well. So we are doing higher dimensional computing. So, we want people who can reliably make, good spatial light modulators, things like that, So indeed, agencies who are working on products which perhaps they don't see that it's relevant, we need to discuss more about the fact that, these things are actually not magically appearing on the table or in a box. And that is where the dialogue has to happen, really. Because at the moment, of course, we are very much restricted to the manufacturers who we have been knowing from our PhD and postdoc days, who are not here in India.
Excellent. Thank you so much for the comments and your insights. And thank you, Maitra, Dr. Murthy, and Professor Sinha. It was excellent talk. If there are, I think we're out of time, but if there are any questions, maybe a couple of minutes, Manjesh. I don't know if we can stretch.
So actually we are out of time. Sorry to interrupt. I think we can extend just 3 to 5 minutes. That's it. Any questions from the public? So participants, speakers, happy to take the questions. If you have any questions, you can turn on your mic or drop your questions through public chat. So I think there is no questions.
All right, then I think we can close. Thank you once again for the opportunity for this presentation, as well as for the panelists for their excellent views. Okay, so thank you, Mr. Vivek, for moderating this session. So I thank Mr. B.K. Murthy, Dr. Urvashi Sinha, and Dr. Arpita Maitri for being part of a wonderful panel discussion. So I request participants to join upcoming session at AISS 2020. Thank you, one and all.
Thank you very much.
Thank you very much. Thank you. Bye-bye.